before I dive into the presentation, a quick history of overlay networks for DDoS mitigation. In the early 2000s, researchers proposed using overlay networks, application layer meshes of filter-capable nodes, to protect servers without changing core internet routers. Secure overlay services pioneered this approach by hiding the real server behind secret access points and filtering all other traffic, at a cost of roughly doubling latency. Soon after, the resilient overlay network showed that multi-hub rerouting through alternate nodes could maintain or even improve performance when direct paths failed. These foundational designs demonstrated that overlays can both absorb attack traffic and dynamically reroute around failures. Upon this insight, I will present my work on resilient overlay network for DDoS mitigation, a simulation-based approach. In this presentation, I'll walk you through our approach to defending against distributed denial of service attacks while using an overlay network architectures. I'll cover the system design, implementation details, and most importantly, the experimental results that demonstrate the effectiveness of this approach. Let's start by understanding the problem. DDoS attacks often continue to be one of the most significant threats to online services today. These attacks overwhelm target servers with traffic from multiple compromised systems, making services unavailable to legitimate users. The statistics are concerning. Attack volumes exceed 1 terabit per second, and downtime costs average 22,000 per minute for enterprises. Traditional defense mechanisms often introduce significant latency and lack adaptability to evolving attack patterns. They are essentially static solutions to a dynamic problem. Our solution is a resilient overlay network that acts as an intermediate protective layer between clients and servers. The key feature is our decentralized decision-making approach, which makes the system highly adaptable to changing attack conditions. Four primary mechanisms drive this resilience: dynamic routing algorithms that find optimal paths around congested areas, intelligent load balancing that distribute traffic to prevent bottlenecks, effective traffic filtering for attack detection, and adaptive queue management to handle traffic surges. This diagram illustrates the high-level architecture of our system. At its core are the overlay nodes that form a protective mesh network. These nodes sit between legitimate clients and the protected server, intercepting and filtering attack traffic. The overlay nodes are the heart of our defensive infrastructures. They are organized in a mesh topology to maximize path diversity, which is crucial during attacks when some paths may become congested or unavailable. These nodes perform several critical functions: packet forwarding with dynamic routing, DDoS attack detection and filtering, traffic load balancing, and continuous health monitoring of neighboring nodes. We can classify overlay nodes into three functional types: ingress nodes that serve as entry points for client, relay nodes that handle internal forwarding, and egress nodes that deliver traffic to the protected server. This separation of concerns allows for specialized behavior while maintaining a cohesive defense system. The first key mechanism is dynamic routing. This allows our network to route around congested or attacked segment. Each node maintains a routing table that's continuously updated based on health metrics from neighboring nodes. The routing algorithm uses a weighted health scoring system that considers multiple factors: latency, packet loss, and congestion levels. When a node's health deteriorates beyond a threshold, the system automatically reroutes traffic through healthier alternatives. Complementing this is our load balancing approach. Rather than always using the optimal path, we distribute traffic across multiple paths using a probabilistic method. During attacks, this balancing becomes more aggressive, creating unpredictability that complicates attackers' ability to target specific resources. Our security mechanism consists of two main components. First, attack detection uses rate-based monitoring with configurable thresholds. We analyze traffic within sliding time windows and maintain source tracking to establish behavioral baselines. Once potential attackers are identified, our traffic filtering mechanisms come into play. We implement source blacklisting, per source rate limiting, and collaborative filtering where nodes share attack information to implement network-wide defense. The system is implemented in Python, providing a flexible and extensible simulation framework. We use the modular design with inheritance to share common functionality across different node types. The core implementation consists of several key classes that model network entities and their behaviors. The node class provides base functionality, while specialized classes like overlay node extend these defense capabilities. For example, the overlay node class extends the base node with routing, packet counters, blacklist, and health monitoring. This inheritance-based approach allowed us to maintain clean code while implementing complex behaviors. For our experiment, we configured a network with 5 overlay nodes in a fully connected mesh, one client generating legitimate traffic, one protected server, and 20 attacker nodes. This topology provides sufficient complexity to test defense mechanism while remaining computationally feasible. We define link properties to model realistic network conditions with overlay links at 100 megabits per bandwidth and 10 milliseconds latency, and appropriate variations for client, server, and attacker connections. Our traffic generation included legitimate traffic at 100 packets per second and attack traffic at 5,000 packets per second per attacker, creating a cumulative attack volume of 100,000 packets per second. We define three primary scenarios: a baseline with normal operation, an attack without defense to demonstrate vulnerability, and an attack with defense to evaluate our approach effectiveness. Now, for the results which demonstrate the effectiveness of our approach, this table summarizes our key findings across the 3 scenarios. In the baseline scenarios, we achieved 100% client success rate with just 1.48 milliseconds of latency. Under attack without defense, performance degraded dramatically. Success rate dropped to 66.49%, while latency increased to a staggering 759.25 milliseconds, making the service essentially unusable. The most important result is the performance under attack with defense mechanism enabled. Here we maintain a 97.43 client success rate with only 6.37 milliseconds of latency. And these results were the same across the different scenarios that we run. Um, that's a that's a dramatic improvement over the undefended scenario. And these graphs illustrates the comparison visually. As you can see, our defense mechanism successfully preserved service quality during attack conditions, with metrics remaining close to baseline levels despite the ongoing attack. Analysis of individual defense components showed they work together. Dynamic routing improved throughput by approximately 31%. Load balancing reduced peak congestion by about 42%, and our attack detection system identified over 90% of attack sources within the first few seconds. A technical improvement. Several technical improvements contributed to this result. Adaptive queue management dynamically adjusts queue sizes during attacks and implements priority handling for legitimate traffic. Performance optimizations include batch processing to reduce per packet overhead, efficient data structures for O1 lookups, and a tier detection strategy that performs simple checks before complex analysis. Enhanced routing the enhanced routing algorithms incorporates direct path preference for server-bound traffic, historical trend analysis that considers past performance, and stability mechanism to prevent route flapping. Defense component contributions. To summarize our contributions, we developed a flexible modular architecture for DDoS mitigation that implements dynamic defense mechanisms with empirically validated effectiveness. Our results show near baseline performance during attacks with 97.4% success rate and only 6.4 milliseconds latency. And we acknowledge several limitations, including abstractions of some network details, limited authentication implementation, and constraint on experiment scale. Future work will address these through enhanced authentication and hopefully introducing machine learning for attack detection, hybrid defense approaches, and real world implementation and testing against adaptive attackers. Thank you.